Swayam Prabha. Digital India. Educated India.
The session S341, Energy Storage and Integration. I am Sang Hong Kim from Tokyo University of Agriculture and Technology. I am chairing this session. So first presenter will be Surasep Kalahum. It's very difficult to pronounce, so sorry for the long pronunciation if it happens. And the title of his talk is Zinc-Based Batteries, Energy Storage for a Circular Economy. And virtually, he will attend this conference. And before the start, I'd like to introduce the presenter. He is an associate professor in the Department of Chemical Engineering, Faculty of Engineering, Chulalongkorn University in Bangkok, Thailand. He received Bachelor of Engineering in Chemical Engineering at Chulalongkorn University in 1997, and then started his first job there for 2 years. After that, he spent 5 years in Japan for master and PhD courses under the guidance of Professor Masahiko Hirao. He received a PhD from University of Tokyo in 2004. Since then, he joined the Department of Chemical Engineering at Chulalongkorn University. His early research was on the use of mathematical tools to support control, operation, and maintenance activities in chemical processes, and to investigate significant phenomena in industry or chemical processes. His current research focuses on the development of next-generation batteries, such as zinc-air batteries and zinc-ion batteries. He has authored a number of articles in peer-reviewed journals and is a frequent speaker at international meetings on energy storage techniques. Besides, Dr. Surasep has been a research advisor and mentor to various undergraduate students, graduate students, and postdoc associates. His research interest includes chemical engineering, process control engineering, burning process design under uncertainty, and multi-object optimization. So, are you ready, Professor?
Thank you very much. So, wow, you can hear me clearly, right?
Yes. So could you share your slide?
Yeah. Okay.
Okay,
so
we can see.
You can see my screen, right?
Please
slide?
start. Yes, we can see the slide.
Yeah, the pink one. Okay,
yeah.
Thank you very much. Thank you again, Mr. Chairman, for your nice introduction. So I'm Surasep Kalahum from Chulalongkorn University, and today my talk is on zinc-based battery as a energy storage for a circular economy. So let me start my talk from this picture. If we look at our planet from space during the night, we see many bright spots, indicating the place where electricity consumption is intense. There are two reasons for the dark area. First, there are no people living there, or there are people living in that area. However, electricity cannot be accessed. For such a case, for the latter case, giving them accessibility to electricity is a precious gift. And we all know that consumption of electricity produced from fossil fuel create various global environmental problems. So renewable energy sources are preferable. Though technologies regarding harvest and conversion of renewable energy are significantly advancing, we can effectively produce electricity via wind turbines and photovoltaic cells at a fraction of cost. We can produce electricity and feed to the power grid. However, remember that there's no inventory in power grid. Even we install more PV, photovoltaic cell, but we cannot respond to the electricity need during the nighttime. To address this issue, we need energy storage system. In terms of cost, a pump hydro energy storage, in short PHES, is the cheapest option. However, PHES requires high high initial investment. Also, installation of PHES is geographically limited. Electrochemical energy storage, such as rechargeable batteries, is preferable. Batteries need two electrodes of different potentials. Basically, batteries store energy in a form of chemical energy and convert to electricity. We can treat a battery as a storage system for electrons. So, wow, the battery is a storage system for electrons. We need two electrodes having different electrode potentials. Of course, highly reversible reaction is preferable. If you want to build a battery having very large capacity, we cannot rely on scarce or rare materials. If your technology use rare metals such as platinum, later you will have problems when we scale up the system. In my lab, I won't allow my student to touch it. Zinc is a good option, as zinc is the fourth major production metal. The production of zinc is over 12 million tons per year. Zinc is cheap and abundant, and it has a stable supply chain. Moreover, it has variable redox potential, high stability, and a high capacity. On top of that, zinc is 100% recyclable, and the recycled technologies are already available. So zinc has been used in batteries very long time ago in primary batteries. We have zinc carbon and alkali batteries. Both systems are very common. Both systems use zinc and manganese oxide as active material. For zinc carbon batteries, ammonium chloride solution is used as electrolyte. In comparison, potassium hydroxide is used in alkali batteries. Though the production and consumption of zinc carbon and alkali batteries are huge, we do not much pay attention to primary batteries. We focus on secondary batteries. There are a number of possibilities for rechargeable zinc-based batteries. They are rechargeable alkali, zinc nickel, zinc air, and zinc bromine batteries. Moreover, zinc ion batteries are also under development and receive much research attention recently. So, zinc air batteries, or we call in short ZAP. Zinc air batteries or ZAP show high potential for large-scale energy storage. This system uses zinc and oxygen directly from the ambient air as active material. So we use zinc to store electrons. Once the battery discharges, the electrons are stored in the form of zinc oxide. The underlying reactions for discharging process involve oxidation of zinc at the negative electrode and reduction of oxygen, so-called oxygen reduction reaction or OR. During charging, zinc is reduced, and at the positive electrode, we have oxygen evolution reaction, in short OER. Typically, we use alkali aqueous electrolyte. Moreover, both zinc and zinc oxides are solid, so handling these species are not an issue. Those apps exhibit high potential for various energy applications. However, several barriers impact the practical application of rechargeable apps. Our group has focused on overcoming these issues with different strategies. Passivation of zinc electrode with zinc oxide, which is the discharge product, shape change and migration as the charge-discharge cycle continues. Dissolution and deposition of zinc are repeatedly occur. Zinc tends to deposit at different locations and in different morphology. This issue affects performance and stability of the batteries. Next, dendrite growth. This is notorious issue of zinc electrode. At high current density, especially in alkali electrolyte, or in a condition where zinc deposition is limited by mass transport, zinc tends to deposit in a form of dendrite and penetrate separator, causing short circuit. And the next issue is corrosion. Corrosion of zinc. Zinc can react with water produce hydrogen. In other words, zinc can donate electrons to water molecule instead of giving to external circuit and oxygen at the air electrode. This is parasitic side reaction. Corrosion of zinc leads to losing of electrolyte and zinc without producing electricity. And the last one, zincate crossover. The discharge product is zincate, and it can transform to zinc oxide. If zincate ions move across the cell to the air electrode and precipitate into zinc oxide at the air electrode, the zinc oxide can block the air channel and passivate the active site of the catalyst. Our group works on these issues using different strategies, such as using flowing electrolyte, developing modified anode for passivation inhibition, using electrolyte additives, and even developing an ion exchange membrane. These are some of our work addressing the issue. Now we look at the positive electrode of zinc air batteries. The positive electrode or air electrode is also significant. ORR and OER are involved during discharging and charging processes, respectively. Actually, these ORR and OER are common in different energy devices. For example, in fuel cells, half of the system is ORR. In electrolyzer and CO2 carbon dioxide reduction system, half of the system is OER. Both reactions are sluggish and has high over potential. We need electrocatalysts for both OR and OER. Typically, OR electrocatalyst is not stable in oxidizing condition. Also, OER is not stable in reducing condition. Noble metals are excellent OR catalysts, but they are too expensive. Metal oxides, such as manganese oxide in certain phases and form, exhibit excellent OR performance in strong alkaline electrolytes. We are also working on metal organic framework and covalent organic framework. You can refer to our recent articles here with this DOI. For OER, ruthenium oxide and iridium oxide are both excellent catalysts. However, again, they are both too expensive. Metal oxides show acceptable performance. Our group is working on layer double hydroxides. Layer double hydroxide are excellent OER catalysts, and they can be fabricated as a self-supported structure, which exhibit excellent stability. Our recent article can be referred here. It's on layer double hydroxide. Besides the catalyst, structure of the air electrode is also significant. Generally, the air electrode consists of gas diffusion layer and catalyst layer. As OR is three-phase reaction, we have to manage hydrophobicity and hydrophilicity of the electrode. Our group is working on tri-electrode configuration of ZAPs. We use separated electrodes for charging and discharging and common zinc electrode. This system exhibits excellent stability for charge and discharge. Moreover, we can optimize OR and OER independently. The cell we are currently developing can discharge stably even at 100 milliamp per square centimeter. And now we reach the area capacity of 150 milliamp hour per square centimeter already. The next topic, I'm going to talk about mechanically rechargeable batteries. Mechanically rechargeable batteries provide a remarkable solution to overcome electrical recharging issue, whereby spent zinc electrodes and electrolytes are physically removed and replenished. We call it ZAFC. ZAFC are refuelable cells in semi-solid form that can be used to store the electroactive components necessary for battery operation in a tank located outside the battery structure. Compared to other types of batteries, such as lithium-ion batteries, zinc air fuel cells offer greater flexibility in terms of energy and power decoupling. There is less mechanical stress on the electrode, enabling the manufacture of long-lasting system. Zinc air fuel cell can be scaled up economically for stationary large-scale application. Since mechanically rechargeable zinc air fuel cells are refuelable primary batteries, they can use relatively simple catalysts that operate only in discharge mode, avoiding the problem of dendritic zinc deposition seen by most electrically rechargeable batteries. Moreover, in order to produce zinc pellets in the zinc regenerator, dendritic morphology is preferred above other morphology. In the research of regenerative zinc air fuel cell, much progress continues to be made. The development of an electrochemical cell system includes a cell housing having an electrolyte capable of carrying metallic zinc, a charging component, a discharging component, and a compartment for storing the metallic zinc. The electrochemical cell system consists of a mechanism for dislodging the metallic zinc and a pump for circulating the electrolyte with the housing plus sensors for measuring both temperature and concentrations of the electrolyte. Such a system can function over a wide range of concentration and current density, and preferably operates in a range of concentration. During charging, as zinc deposits forms on the cathode surface, they can regularly remove and gravity transport downward into anode beds. Once the anode assembly is completely filled, zinc deposits tend to accumulate and gather in the region above the discharging cathode and beneath the charging electrodes. In another system, the system consists of zinc particle regeneration, fuel storage, and power generation for producing electricity. Additionally, the innovative system incorporates a control unit that is designed to independently control the flow of the carrier electrolyte between the regeneration of zinc particles and the subsystem of the fuel storage. The structure is optimized to operate with metallic zinc particles, having a dendritic morphology that can enable the particles to be easily fluidized in the barrier electrolyte and to be circulated throughout the system. The presence of dendritic particles in the distributed flow system has some advantages. First, dendritic shaped particles are more fluidizable and have better transport property than compact bolder particles, thus aiding the scaling up of distributed system, providing a large range of flow rates while incurring lower energy loss for field transport. The second, the production of dendritic particles occur in a manner in which the attachment to the surface of the regenerator electrode is less robust than planar plated or densely formed particulate formations. Such a process benefits the removal of particles from the electrode surface since less energy is required. Previously, dendritic particles had to be cleared away by scraping the electrode surface. Such procedure in a physical contact with the electrode surface led to increased surface wear and early breakdown of the system. And the last issue, the last item, dendritic particles in distributed flow system have a high surface area per volume ratio. Therefore, the improved kinetics of dissolution of such particles provided enhanced support for a device of higher current density in the subsystem power generation. To evaluate performance of such a system, which integrates zinc airflow batteries and zinc electrolyzer, we developed a mathematical model. The following parameters were investigated: electrolyte flow rate, potassium hydroxide concentration, and zinc cation concentration. Besides, the influence of hydrogen evolution reaction on performance of the system was examined. Upon investigation, it was found that potassium hydroxide concentration had a significant effect on the performance of battery. Further, it was noted that increasing potassium hydroxide concentration enhanced HER, hydrogen evolution reaction, and reduce the current efficiency. However, the optimum potassium hydroxide concentration, which is about 7 molar, provided maximum energy. Increasing zinc cation concentration was able to suppress the hydrogen evolution reaction and increase the current efficiency of the battery because of the lessening of reversible potential difference between the zinc electrode reaction and hydrogen evolution reaction. As regards the electrolyzer, the results show that the performance of the electrolyzer was dominated by zinc cation concentration and electrolyte flow rate. When zinc cation concentration increased together with the flow rate, current efficiency significantly increased. Further, the charge energy was reduced due to the enhancement of zinc cation diffusion to the electrode surface. Yet, increasing potassium hydroxide concentration does not directly improve electrolyzer performance, but contributed to the increment of saturation limit of zinc cation, which enhanced the electrolyzer performance. For the overall integrated system, it was observed that the current efficiency of the integrated system was dominated by the electrolyzer. Therefore, increasing zinc cation concentration and the electrolyte flow rate had a benefit effect on the current efficiency of the integrated system. On the other hand, the energy efficiency of the integrated system was essentially influenced by the discharging cell. Maximum energy efficiency was obtained by the optimum concentration of potassium hydroxide. Overall, it was found that hydrogen evolution reaction had a detrimental effect on the performance of the integrated system. A model-based analysis is one of the effective approaches for the study of zinc-air batteries. This technique, however, requires reliable discharge data as regards parameter estimation and model validation. I recommend two of our articles that you can find high quality data of the discharge of zinc-air batteries. In the first paper, we provide the data required for the modeling and the simulation of SABs. Each set of data includes working time, cell voltage, current, capacity, power, energy, and temperature. In the second paper, you can find discharge profile of zinc-air battery at different flow rates and currents. Each dataset includes current, voltage, capacity, specific capacity, energy, specific energy, and discharge time. So a generic dynamic model of a SAB is a key component for effective battery management and monitoring. SABs show strongly nonlinear behavior, where the steady state gain is strongly dependent on operating conditions. The voltage characteristic of SAB and lithium-ion batteries are compared here. It can be observed that the voltage profile of lithium-ion battery has a distinct slope for discharge voltage and a high slope for open circuit voltage. On the other hand, the zinc-air battery possesses a very flat slope in its voltage profile for both discharge voltage and OCV. Regarding lithium-ion batteries, the differentiation of battery voltage with SOC or state of charge can be discriminated due to its the intercalation mechanism. Hence, the relation between voltage and state of charge is regularly useful for SOC estimation. SOC is a state of charge estimation. On the other hand, for SAB adopts the mechanism of zinc and oxygen conversion, whereby their change of dynamics is lower than that of lithium-ion battery. Moreover, zinc-air flow batteries utilize flowing electrolytes, leading to a more constant electrolyte concentration. For this reason, the voltage and state of charge relation of zinc-air flow batteries is very flat and difficult to be discriminated. It is even more challenging to estimate the state of charge of this type of battery. The study aims to develop a dynamic model being capable of predicting the nonlinear dynamic behavior of a refuelable zinc-air battery using linear parameter varying technique called LPV. The LPV model is constructed from a family of linear time invariant models, where the discharge current level is used as a scheduling parameter. The developed LPV model is benchmarked against linear and nonlinear model counterparts. The LPV model performs remarkably well in capturing the nonlinear behavior of a ZAP. It significantly outperforms the linear model. Overall, the LPV approach provides a systematic way to construct a robust dynamic model which well represents the nonlinear behavior of ZAP. An effective state of charge SOC estimation is essential for the development of a battery management system. At present, the provision of a SOC estimation for zinc airflow batteries is still at its early stage of development. This work sets out to develop the SOC estimator for zinc airflow batteries. The estimator is based on a linear parameter varying or LPV model, integrated with an extended Kalman filter EKF. The LPV model is constructed from multiple linear time invariant models with battery current and SOC as scheduling parameters. As I mentioned to you previously, the response data for zinc airflow batteries have an exceptionally flat profile related to state of charge change. Dynamic differentiation only occurs when state of charge is almost depleted. For this reason, the estimation of SOC converges to the true value when SOC is near depletion. So in this work, it is shown that by appropriate tuning the SOC estimation, performance of the LPV model combined with EKF performs well as the absolute error of SOC. The LPV model with the EKF algorithm is also compared with the Lundberger observer. The proposed estimator can surpass the Lundberger observer estimator. Overall, this SOC estimator provides a systematic way to fulfill the requirements of a battery management system. So let me conclude my talk. I introduced you a rechargeable zinc-based battery, which is especially zinc air battery, which is suitable for large-scale energy storage system. And I introduced you the critical components for rechargeable zinc air batteries. Also, we discussed about OR and OER catalyst development and tri-electrode configuration of zinc air batteries. And I introduced you the mechanically rechargeable zinc air battery. And finally, I show you how PSE, process system engineer, take part, contribute to the development of the zinc air batteries, especially those, the dynamic model and also SOC estimator. Okay, thank you. Thank you very much. And if you have any question, I'm more than happy to entertain your questions. Thank you.
Thank you for the presentation. So now the session is open for the floor. Do you have any questions or comments? Yeah, please.
Thank you, Professor. It was a good talk. I have few queries about, you mentioned that in the zinc air battery, there is a discharge curve would be different than the lithium ion battery. So let us say we are considering any battery management system. So what are the key components we have to look after in case of the zinc air battery?
Okay, let me show you again about the characteristic of, discharge profile of lithium ion battery and zinc air battery. And you see that for lithium ion battery, you see that it's quite, we see the relationship between the voltage and state of charge, right? But for zinc air battery, the problem is the discharge. We have a very flat discharge. So that means, well, the voltage will drop once it's nearly depleted. So why this is a problem? So you know that for example, for your equipment like mobile phone or notebook, and you can see, right? You can track the SOC instead of, you know that now your battery is 50%, 20%, or 30%. But in case of zinc air battery, no, you cannot do that using the same technique because we cannot relate the discharge voltage and SOC. That means, well, the voltage is quite flat. It will not drop even it nearly reach the depletion mode. And once it reach the depletion, it will stop suddenly. So that is a big question. So from our work, we prove that we cannot do that without, even using EKF. But if we don't know the parameter, we cannot do anything on that. However, once we reach the zone, nearly depletion zone, where the voltage depends on the SOC, we can observe that only when the battery nearly fully discharged, about 5%, something like that. And at that zone, if we estimate, we predict the parameter using that zone, of course, in the next round, we can predict the whole horizon of the discharge profile. And we can predict, of course, you can use Coulombic counting. For example, you count the capacity you use at the time, right? But however, because let's say our battery has 100 milliamp hour. However, during discharge, you don't know exactly whether, because it's the discharge capacity depends on the condition you use your battery. If you discharge at very fast rate, you cannot reach that 100% capacity. So Coulomb counting also cannot be used in this case also.
So just a
Did
follow-up.
I answer your question?
But I just have a few queries on that, just if you can. Just because in normal batteries, we actually tend to tell about the state of health using a state of charge. So in this case, I feel little not intuitive, like how you will calculate a state of charge itself. And if the state of health is a function of state of charge, then if we cannot get the value of state of charge from the discharge curve, how accurate would be the state of health? Are you looking into it, or is there an avenues in that?
Well, we have to update the EKF all the time.
Okay.
Yeah, we use the dynamic information.
Okay.
Yeah, for example, you know that even for static information, like you monitor the voltage, of course, it doesn't change on that region. However, if we look at the dynamic behavior, it will be changed. For example, if for the ultimate case, of course, if we have enough time and resource, we can use EAS, impedance spectroscopy, to monitor the state of charge. However, in real situation, we cannot use that, but we can use the dynamic information. That I mentioned to you that we use EKF. Yeah. However, we need a proper parameter for EKF first. We have to train the EKF first, extended Kalman filter. And it proved that extended Kalman filter can be used if we estimate the correct parameter for it.
Hello, Professor. I'm Gunjan. I'm from IIT Madras. My question would be on the experimental data that you just now showed. So is it the data for the first question would be is it the data for mechanically rechargeable batteries, zinc air batteries, or is it electrically rechargeable zinc air batteries?
For those two papers, they are mechanically rechargeable zinc air batteries.
So
of course, in the future, we will publish the data for rechargeable batteries also.
Electrically. Okay. So in that case, how do you, so is it sorry, I missed something in the between in your presentation. Just, can you just repeat that for, so the zinc is flowing as particles, or you have zinc as a anode as a plate in your system, the data that you have given?
Which one? Which from scientific data, right?
Yeah.
Sorry.
The
For scientific data, just one moment.
Yeah.
I'm not sure you can see my screen or not.
I can see your screen. Yeah.
Yeah, right. For these two papers, of course, the data is for mechanically.
Can you go one slide
It's only
back?
the battery, not recharge. Okay.
Can you go
Because
one
we
slide
replace all the zinc particle in the system.
Oh, okay.
Mhm.
Yeah.
Yeah.
Can you one slide back, previous slide than this one?
This one?
Yeah, this
or
one.
This one?
Yeah, no.
Yeah, this
where
one?
you have
Okay.
the complete system. Yeah, this one. So
This one is a theoretical model. It's not. It's we did not disclose the data.
okay. So
This one is a theoretical model for integrated system, zinc air battery and recharge regenerator. Yeah.
Oh, so my question was on this only. So then, because my question was, how do you even get SOC for this system, if at all you get it?
Yeah,
yeah,
this one,
even-
of course, because it is a theoretical model. So we use Coulomb counting, Coulombic counting. You know
Yeah.
how well the amount of zinc we generate, right? Because we know, yeah. And then we keep counting the Coulomb of the counting the Coulomb means counting the electron in this available in the system. Yeah.
Okay. Yeah.
As I mentioned to you that it's the battery, it's a storage of electron. Yeah.
Okay. The next slide, please. Then.
Excuse me.
Yeah.
Next slide, this one or this one?
Sorry, if at all.
I'm sorry. So the time is almost
Sorry.
run out.
Yeah.
So
Thank you for your time. Then.
let's please contact through the email or something. So
Okay. Thank you very much.
let's listen again. Listen to the presenter.
Yeah.
Thank you very much, Professor. Very nice talk.